In the previous lecture of Tiny Systems, we looked at writing a small functional programming language inspired by ML. Today, we're going to look at the other basic approach to programming, which is imperative programming, and specifically, I'm going to be using BASIC as my inspiration. And I will look at BASIC as it was available on microcomputers like Commodore 64. First, I should explain why I'm choosing BASIC and why this particular kind. So Edgar Dijkstra, who's very well known for his comments about everything in computer science, has a quote about BASIC, and he says, "It is practically impossible to teach good programming to students that have had a prior exposure to BASIC. As potential programmers, they are mentally mutilated beyond hope of regeneration." So that's not very optimistic. Why am I doing this to you? Well, you can look at BASIC as a programming language, and then, as Dijkstra says, it's not very nice and very elegant programming language. But what is interesting about BASIC is if you look at it as a programming system. So in the introduction, I talked about sort of the language side, where we just look at the syntax, the sort of features of the language. But I also talked about the interactive programming environment in which the language is always embedded. And if you look at the environment that surrounded something like BASIC on microcomputers, it was actually very interesting. BASIC was one of the sort of first programming languages that many people experienced because a lot of the microcomputers shipped with BASIC. And when you started your computer, what you got was a BASIC prompt. So everyone was in some ways exposed to programming, and BASIC really became part of the early computing culture. There was a lot of magazines around it. But what's also interesting, more as a sort of programming tool, is this mode of interaction with BASIC. That's what I want to show you in this video. For the Tiny Systems course, BASIC is also interesting as a programming problem because if we want to implement BASIC, we will actually use a lot of the ideas that we saw earlier with TinyML, but it will be a little different. So the interpreter will need to have a richer state because in BASIC you have a program that you're editing interactively, and we will want to model that. BASIC also makes a distinction between statements and expressions, which is something that we didn't have to do in TinyML. And we will have to do some handling of state. We will want to work with input and output, so you will also learn some more interesting F# programming through this task. All right, the first thing I want to show you is how does BASIC on something like Commodore 64 actually look. And there's plenty of online emulators you can use. So I'll start with one of those. This is an emulator that's kind of at a more fundamental level, modeling the underlying machine that runs BASIC. So this is really a sort of very realistic emulator where all various clever hacks and tricks that people invented with BASIC, where all of these things work. The slight disadvantage of this is that it's also kind of hard to use. So this will not be as smooth as it could be. But I can write hello world. So when you launch your Commodore, you get this console and you can type in BASIC commands. So you type print hello world, then you run it, and indeed the machine prints hello world. One interesting thing here is that this works both as a prompt and as a code editor. So if I prefix my command with a line and number, then I'm saying, I don't want you to run this immediately, but make it part of a program. And so now it didn't do anything. I can type list, and this prints the program I have so far. There's just one line. I can type run, and then it will actually run the program. And of course, if you want to have fun, that's the sort of classic example of what people did with their machines, we can say, after printing, go back to the line 10. So if I now run this program, it will run an infinite loop with hello world. Okay, you can stop this. So this was one example. I want to show you something a little bit more interesting. So for line 10, I am going to say, what I want to construct is a little program that draws stars all over the screen. And we'll start by saying I equals, and then I want to have some computation, a little calculation that takes a random number. So we generate random number and multiply this by 1000. And I'm choosing a random number that's from 0 to 1000 because the screen has 1000 characters on it. So we want to sort of choose a random position on the screen, and that we do by doing this. And now the other thing I want to show you is this poke command. And what poke does is that it puts a character, well, what poke does really is that it puts a specific value at some location in the memory of the computer. But in BASIC, the memory address of 2024 is the start of the memory that's mapped onto the screen. So if you put something in memory at this particular address, it will just appear on the screen. And if we put 42 as the character code here, then this will put a single star somewhere on the screen. I can run this, and indeed a little star appeared here. So if we then run this in a loop, we will get a little program that puts stars all over our screen. So there's one interesting thing, which is this poke command for accessing memory, and I'll say more about this in a second. There's another interesting thing that I want to show you. So the character code for stars was 42. But what if we wanted to use plus, which is 43 instead? The interactive prompt that I'm using here, as I said, works both as a kind of prompt where you can run commands, but as an editor. And if I start with the line number 20 again and say poke 1024 plus I 43, I just entered that single line and I list my program. Now the program has been modified. So you can sort of modify the program line by line. And if I run it, now we have little pluses appearing everywhere. And in BASIC, this is actually sort of this basic mode where you have the editor is taken even further, because I can navigate around the screen and I can sort of put things anywhere on the screen. Like I can go up and remove the pluses if I want, for example. But I can also go to a line that has the code, change this back to 42, and if I hit enter now, what will happen is that BASIC will read the current line and run it. So now I can sort of scroll here again and say run, and now again we have stars appearing. So this mode of interaction is something that's very interesting about the BASIC programming system. And it's really the system that matters here, not just the language, although the two things have to work together. This only works because BASIC has this line-based programming model. So what is really interesting about BASIC? I think there's at least three different things. One is the learnability. So when you bought a microcomputer, the computer booted directly into BASIC prompt, and this was a thing that kind of led a lot of people to try programming. And it's a sort of characteristic of the system that very few programming environments these days can give you. The way people were distributing games was also interesting, because the typical way of getting some basic games to run on your Commodore was to buy a magazine, like the one here in the picture, and copy the source code line by line into your computer. And again, this sounds extremely tedious, but it was something that kind of got people curious about programming. And as you were typing the programs, of course you made mistakes, and you then had to find out what's going wrong. And through this, you could very easily learn how to program BASIC. So this is more about the kind of environment and the way BASIC was used, but it's really an interesting characteristic. Looking more at the programming system, BASIC had this idea that it's going to be very simple for novice programmers, for people who are just learning things, to write some basic programs. And I think that's largely the case. The core language is very simple. It doesn't let you write super well structured code, but it works for simple tasks extremely well, and this interactivity helps. But also, BASIC was not something that was strictly limited to just people who want to do simple things, because it had these kind of extra escape hatches that you could use if you were a sort of more curious hacker and you knew what you were doing. The poke command in BASIC lets you write numbers, bytes, into arbitrary place in the memory, which can be used for putting things on the screen, but it can also, there's a sibling command called peek, which reads a thing from the memory. So you can scan the memory. You can even find your source code stored in the interpreter memory, or in the Commodore memory, and modify the program. There's also a sys command that starts executing instructions from the memory. So with these two things, people who wanted to do some advanced, interesting things with the system had a lot of power to do these things. So there's this kind of structure of the system that enables this sort of progression from basic tasks to very sort of interesting hacking. And the other thing which I was showing in the interpreter is that BASIC had this interactive mode where you interacted with a terminal that served both as a REPL, where you can run commands, and as a code editor, where you can edit your program. And this whole thing was integrated in a sort of single environment that was relatively easy to use. And if you compare this with how programming environments work today, where you have sort of editor on one side, maybe terminal with a REPL somewhere else, and then plenty of other things, I think that integration was really interesting and quite powerful. So I find this very interesting, and some time ago I created this online essay that illustrates some of these interesting aspects of Commodore 64. And for that essay, I wrote a tiny implementation of BASIC, which is what has inspired this part of the course. And I'll sort of quickly show you how this works. But the point of this was not to create like full exact reconstruction of Commodore 64 BASIC. It was more to kind of have enough of an implementation of BASIC that can show this interactivity and this kind of interaction with the terminal. So that's a thing it does accurately, but there's plenty of things that it doesn't do. So it doesn't store programs in a memory in the kind of same way as Commodore did. You can't use poke to modify memory. There's just like a little variant of poke for putting things on the screen, but not in the same way as it worked in the original system. So if I go to this essay, then sort of has a guided tutorial on using the system. But again, I can do the basic things that I was doing before, print hello world, or do an infinite loop, printing hello world, and run it. So all this works. There's sort of in the essay, if you want to play with it, there's a lot more you can do. One example is this famous example of a maze that's generated with a basic code. This with a bit of effort you can put on a single line. And the way this works is that it just generates slashes and backslashes alternatingly. But the way the slashes were rendered in BASIC is that it sort of connects nicely and generates this infinite maze. So in this tutorial, what this eventually constructs, and I'll just scroll down to the final result, is this little game that we can load and run. So the game is you have a ball running around that bounces off the walls, and you have to catch it with this pedal here. And if you don't, then you lose and you get a game over. What I think is interesting here is that the way the basic programs are structured, the way the environment works, makes it relatively easy to kind of enable or disable parts of the game. So if I list the source code, well, there's some state initialization, then it goes on, there's moving the pedal, and so on. So there's quite a lot of code here. I can also list only parts of it, and this kind of relies on using the line numbers in a clever way. So if I list everything from the start to line number 2000, then that's my code for initialization here. Then everything from 2000 to 2500 is my code for the ball movement, and from 2500 until I guess the end is moving the pedal, and then the game over. The reason why this is using thousands, and the reason why you always tend to keep 0 at the end, is when you want to insert a line in between two existing lines. It's useful to have sort of 10 numbers available in between the lines. So that's one of the sort of basic tricks that programmers learned very quickly. Now, what's interesting here is that, for example, if I just wanted to debug the pedal movement without worrying about the ball, because then I get game over if I don't catch it, I can find the bit of code that that sort of jumps back to the next iteration of the game here. So this is jumping back to 2000, which was where the ball movement happened. And if I change this line and say this should jump to 2500 and run my program again, then I sort of skipped over the lines that deal with the ball movement, and I can happily debug my pedal and make sure it doesn't go off the screen, for example. And then I can sort of stop my program, go back and modify it again, run it, and again play my game. So the point of this was there's interesting aspects of this interactive REPL style environment that existed in BASIC that we don't have in current programming systems, and maybe in some ways they could be recreated. So that was a sort of introduction to the programming system of BASIC. And Before we continue, I would like to say a little bit about reasoning about basic programs. Because when Dijkstra complained about BASIC, the main argument was that it's not a language that you can easily think about. Like when you have basic program, it's kind of hard to understand what it does. But this is not something that sort of remained the case forever. There's various ways of reasoning about programs, and I think when you think about what basic programs do, it's useful to be aware of that. So previously, in TinyML, we had a small functional language, and thinking about what a TinyML program does is quite easy because it has this compositional semantics. It means that if I have a term E1 that has some meaning and term E2 that has some meaning, I can define the meaning of a composite term in terms of the meanings of these two subterms. So whenever you have an expression-based language without side effects, you get this nice property that you can reason about sub-expressions and then use this understanding to understand the bigger thing. This doesn't really work with imperative languages like BASIC, because, well, what's the meaning of print high? That, okay, we have to sort of realize there's some side effects going on. But then if I have something like go to 10, you can't really say what that means in isolation. In practice, it's whatever the interpreter does. But what if you want to have some formal reasoning? And I think this is interesting because you will see this reflected in our implementation of BASIC. When we wrote TinyML, all the evaluation was just given an expression, reduce it to a value. So the meaning of the expression was always defined just by the expression itself, modulo some variables in scope. In BASIC, the meaning, what the interpreter has to do is depending on much more sort of richer, complex context. So what go to 10 does depends on what is at the line 10. And if we want to write the interpreter for it, we have to look at the line 10 and find the code and run it. So this complicates proving properties of programs, which is what Dijkstra was interested in. But not all hope is lost. There's mechanisms for reasoning about imperative languages as well. In TinyML, I told you a little bit about operational semantics because that's how you understand functional programs. Here, I'm going to tell you a little bit about Hoare triples, which is a mechanism invented by Tony Hoare for reasoning that can talk about imperative programs as well. And it uses this notation where you have in curly brackets P and Q around some command C, and those are precondition and postcondition. So the precondition P says what is true before you run the command, and Q is what is true after the command is executed. I have this little program here as an example that calculates a factorial. So Q is the number that we want to calculate. So if we want 5 factorial, we will sort of start by setting Q to 5. N is the number of iterations we run so far, and F is the factorial so far. So this will sort of initialize and then loop until N equals Q, and in every step it will increment N by 1 and multiply the factorial by the current number, and then at the end we print F. And you can actually use the preconditions and postconditions to reason about this. Here I have a little annotated version of the same program where initially we have no particular preconditions. After the initialization, what holds is that F is a factorial of N. That's true because, well, F is 1 and N is 1. And then there's this sort of condition where, again, like every time we jump to the line 40, it holds that f is a factorial of n. And on line 50 and 60, we calculate the new state. So we calculate f prime and n prime as new versions of the new values of those variables. But it holds that if f is a factorial of n before, then after running these two commands, the new f is a factorial of new n. And this works because we increment n by 1 and we multiply f by n. So and then the key thing here is that you can kind of reason about the program by checking that the post conditions of something before hold or are the same as the preconditions of the thing that you do after. So if on line 70 we have this go to 40, this works because previously the post condition of the two lines before was that the new f is a factorial of the new n, and that's what's required by the next step of the iteration. And so at the very end, when we reach the printing, we know that f is a factorial of n, and because the only way to reach that line is by this jump from the line 40, which only happens if n is q, we also know that n is q, and so we calculated the factorial of q. So this is how we reason about basic programs, and it's just a bit of theory to illustrate that there's sort of formalism and mathematical thinking that can be applied to BASIC as well. But we're not going to do more of formal reasoning about BASIC. We're going to look at how to implement the interpreter for it.